Okay.
What ODP are we on? 20 now? I think it's 37.
Yeah, you missed all the other ones. Yeah, so ODP today, another ODP tomorrow. Tomorrow's ODP is going to be Fibonacci numbers, but I'm going to ask you to cache your results. I'm going to ask you to do long ints instead of just ints, so we can go up a lot higher. Not a lot higher, but up to like 60 or something. So, all right, so dynamic programming. Let's talk about one more example of dynamic programming. This is a fun one. This is related to dropping eggs out of windows. So, so that's always cool. So here's the setup. You have a series of eggs, and your eggs are all identical. And you're trying to find what is the highest floor that you can drop an egg from without it breaking. And it could be, you know, you're in a 50-story building, it could be the 20th floor is the highest you can drop it from. That's a really good egg. It might be that you can drop it from the 50th floor and it survives. Or it might be that if you drop it from the first floor, it cracks, right? And the safest floor would be like, you know, the ground floor. And there's some niceties here. So all your eggs are identical. If an egg survives from a given floor, it will survive from any lower floor as well. If it breaks at a given floor, it will break at any higher floor. So kind of the expected behavior for eggs. And dropping an egg that survives means you can reuse it, and it's completely identical to the original egg. It doesn't suffer increasing damage. Okay, or if you like, you can trade it in for a new egg if it didn't crack. So the setup is you're in a building that has a certain number of floors, and you have a certain number of eggs. 1 egg, 2 eggs, 3 eggs, something like that. And your goal is to answer this question, what's the highest floor from which we can drop an egg without it breaking? And the question is, what's the best number of trials that you can use to answer this question? Can you always answer this question with 15 experiments? Do you need 16 experiments? Do you need 20 experiments? And it depends on the number of eggs and the number of floors, obviously. So let's suppose that you have a single egg and you have 10 floors. And you only have 1 egg. And you want to know what's the highest floor I can drop it from without it breaking. Oh, no projector. I wondered what you said. Yeah, you really got to start from the bottom floor, because if you start anywhere else and you drop it and the egg breaks, you don't know what the magic floor was and you don't have any more eggs to work with. So if you only have 1 egg, it's going to take you 10 experiments. Try dropping it from the first. If it survives, drop from the second all the way up to the 10th. You're getting a lot of stair climbing here. Now once it breaks, you're done. You know, if dropping from the 4th floor causes it to break, you found your answer. Highest floor that's safe is the 3rd. You don't have to do the other experiments. But worst case, it might take 10 experiments. You drop it from the 10th floor and it survives, and now you know I can drop it safely from the 10th floor. So for 1 egg, the worst case number of experiments you need is the number of floors. But what if you have 2 eggs? Okay, we can drop it from the middle floor. And if it survives, then we know our answer is somewhere between 1, 2, 3, and 4. And we have 2 eggs left, right? Sorry, if it survives, we know our answer is somewhere between 6 and 10. And we still have 2 eggs left, okay? But if it breaks when we drop it from floor 5, we've only got 1 egg left and we've got 4 floors, and we've got to do 4 experiments for that. So it's going to take us 5 experiments, worst case. Can we do better than that with 2 eggs?
Once you drop your first egg, if it doesn't break, then you can put it down again by going up.
Right. But with that algorithm, the most number of experiments we'll need is 5. There may be a case where we'll need 5 experiments to answer the question. So is there a different algorithm where the worst case is going to be better than 5? Is there a different algorithm where we might be able to answer this question in all cases with 4 or fewer experiments. Start from the top. Well, if that breaks, then we've got 1 egg left and we have to do 9 experiments. So that's going to take a total of 10. And that's worse. Kind of seems like that's the best, but what? But you do have 2 eggs. Then you're out of eggs. But you haven't answered your question, what's the highest floor you can drop it from safely?
So it's really short, no answer.
Yeah.
Just break them both, right? 2 eggs.
So if you drop the first one from the top and it breaks, you've only got 1 egg, and you've got to figure out which floor, 1 through 9, is the highest safe floor. And the only way to do that is try first, second, third, fourth, fifth. And if it turns out to be the 9th, that's going to take you a total of 10 experiments. What would happen, and I'm asking because I don't know yet, what would happen if we started with the 8th floor? Sorry, no. What happens if we start with the 3rd floor? The egg will either break or not break. If it breaks, then we have to try the 2nd floor and the 1st floor. We only have 1 egg, so we have to try 1st and 2nd. That's going to be a total of 3 experiments. But if it survives from the 3rd floor, now we have 7 floors and we have 2 eggs. So now if we were to cut it in the middle, I don't know if that's the middle, I guess this is the middle. Drop it from floor 7. Well, if it breaks, we know the magic floor is either 4, 5, or 6. That's going to take 3 experiments. So that's still going to be 5 experiments. Okay, let's try a different one. Suppose we start with the 4th floor. If your egg breaks, now you have to take your last egg and try 1, 2, and 3. So that's a total of 4 experiments. If it survives, you've got 2 eggs and you've got 6 floors to analyze. You've done 1 experiment. So I don't know, let's try the 7th floor. And if it breaks, that's your 2nd experiment. Now you have to try 5 and 6. That's going to be a total of 4 experiments. If it survives, that's 2 experiments. You have 2 eggs. You have 3 floors. So let's try floor 9. That's your 3rd experiment. If it survives, then you drop 1 from 10, and that gives you your answer. If it breaks, then you already know your answer is floor 8. So 3 or 4 experiments get you your answer. So there's a better solution than 5. You can do it in 4 experiments by starting with the 4th floor. So what if you have 100 floors and you have 7 eggs, right? This is really, really painful to try to analyze like this. Very easy with dynamic programming. So this whole thing begins with a first experiment. And the first experiment is taking 1 egg and dropping it from 1 floor. And that floor could be anywhere from the 1st floor to the top floor. And there's exactly 2 possible outcomes. So for f equals 1 to the top floor, if egg breaks, then we have 1 fewer egg, and we know that the magic floor is somewhere between 1 and f. If the egg does not break, we have the same number of eggs, and we know the magic floor is somewhere between f plus 1 and the top floor. So we can write a function, egg, floor, comma, eggs. So you have f floors and e eggs. And we can say, let me call this, yeah, I'll use a different variable here. So for I equals 1, 2, F. Well, if the egg breaks, then we need to find out, given E minus 1 eggs, how many experiments do we need for top minus F plus 1. Sorry. Number of floors minus I plus 1. So let me see if we got the fence post right. So if I is equal to 7, then we need to solve this for 3 floors. Okay, so it's just F minus I. Okay, if the egg survives, then we need to look at the same question for E eggs because our egg didn't break, and we need to ask this question on I minus 1 because the magic floor is somewhere between the ground and the floor below, the one we just tested. So for each floor from 1 to the top floor, we simply find the maximum of these two values. That's the worst case number of experiments we need if our first drop is from floor I. And we just need to minimize this maximum. So find which floor gives you the smallest maximum of these two experiments. And it's completely recursive. So ask the user how many floors, ask them how many eggs, put that into floors and eggs, and I'm going to call my egg function floors comma eggs and print out the fewest number of drops required. So let's look at the egg function. It fits on one screen. That's good. Okay, so if you have one egg, the answer is it's however many floors you have. That's one of our base cases. If your number of floors is less than or equal to 0, the answer is 0. You don't have to do any experiments. And if you have exactly one floor, the answer is 1. You simply drop it from that window, and if it breaks, then it was the ground floor that was the tallest. And if it doesn't break, then that floor is the tallest. So those are 3 base cases. The general case is the following. So for your floors from 1 to the number of floors. So if the egg breaks, right, then you're going to have to find which of the floors below you is safest, and you have eggs minus 1 eggs, right? And the total number of experiments will be however many experiments it takes to answer this question. Okay, with eggs minus 1 eggs, what's the tallest floor between the ground and current floor minus 1? That many experiments plus 1 more because we just dropped an egg from floor F. So that's the worst case number of trials if the egg breaks. And if the egg doesn't break, then you have to use those eggs, number of eggs, on the floors above you. And whatever the number of trials is for that, add 1 for the egg we just dropped. That's the number of trials required if the egg survived. So we want the largest of those. That's the worst case. So this is the worst case number of experiments we need if we make a drop from floor F. And inside this for loop, we keep our best answer, right? The best worst case. Initially, it's the number of floors. But if this answer is smaller than our best, we'll keep that. And then we'll just return that as our best answer. And I've hobbled the caching of our results here, right? So normally I'm going to save our result in a 2-dimensional array indexed by floors and eggs. And in the beginning, if that's bigger than 0, we'll return its value. Otherwise, we'll go ahead and recurse. But I've taken that out for a first cut. So 10 floors, 1 egg, fewest number of drops is 10. All right, 10 floors, 2 eggs, fewest number of drops is 4. And here's all the experiments that it had to run. So a fair number. So 257 experiments. So 20 floors and 3 eggs, and it's off and running. And I don't know if this ever finishes.
Just take into consideration if you've proven that 6 won't break, and then you try 8, and that does break. It doesn't do another additional experiment for 7.
We're going sequentially. So that for loop is starting with 1 and going up to the top floor. So it's not going to test a drop from 8 until it tests it from 7.
Okay. So it's not doing that thing that you were talking about, where you try 4 and then you split that again.
No, it's being much more direct. All right, so 20 floors, 3 eggs. Looks like it takes a total of 5 experiments. Let's see how many times it had to recurse to figure that out, though. So 2,621,441. So you run this on even a modest-sized problem, it's never going to finish in a reasonable amount of time. So you throw in your dynamic programming, right, 2-dimensional array, and I put a maximum of 500 floors on it. And inside, we check that array, and if it's already calculated the answer for that many floors and eggs, it just returns it. Otherwise, do the recursion, save the result. So now it gets your answers pretty quickly. So 500 floors and 30 eggs. And it's still got some work to do. 9 drops.
The first time you ever made this program, saving a dimension array and only counting, does that mean you have to do it with that many eggs and that amount of floors before it remembers that and it's actually helpful?
Let me see if I can parse that. Say it again?
Sorry.
Sorry. Okay. So egg is a program that's given a number of floors and eggs, and it returns the number of experiments you need. Okay, that whole thing is caching its results. So the first time that you try to drop 3 eggs from a 20-story building, right, it will do whatever it has to do to find an answer. But once it's found it, it will save the answer for 20,3. Okay, and if you're actually working on a bigger problem, and as part of that problem, it needed to do 3 eggs from 20 floors, right? That second time, it will take the answer that you saved in memory and just use that.
Okay, so if you did 21 and 3, it would save the 20 and stuff to recurse.
Yeah.
Okay.
Right. So this is pruning the recursion tree, because I've never tried drawing a tree for this, but it's kind of like Ackerman's function. It's going to be really hairy, wide.
So now that you've done 500, does it still remember?
No, it's just during the run. It's just saving it in memory. So if we do the same thing again, it's going to have to go through all of those steps again.
So if you put in more eggs, does it go quicker? Does it have more potatoes?
I don't know how it grows depending on floors and eggs, so let's do 100 floors and 100 eggs. So that still takes 7 experiments.
After a while, you're going to get diminishing returns on the number of eggs that you have.
Yeah. So let's do 100 floors and 50 eggs. So that takes 3,600. And if you have more eggs than you have floors, I don't think it's going to affect your answer. But I can't promise that.
Just means you can try each floor twice if you weren't sure.
Yeah.
Did that break?
That was fun. Let's do it again. Yeah, so extra eggs won't help you. So this is a fun problem, and it's classic dynamic programming. It's repeated substructures, right? The cases that you have done before get done a lot, right? So go ahead.
Pipe tail will get you the end of the execution.
Yeah, so tail reads the last few lines of whatever it's getting from standard in. So if you pipe something into tail, when that command exits, then tail will print out the last few lines. So, and that short circuits all of this output. So yeah, 2 eggs, 2 floors, for example, gets called a lot, right? And 3 eggs, 2 floors, and 2 eggs, 3 floors, and all these base cases get called a lot. Yeah. Yeah, you could do that. You could just write it out to a file and then pull it in to memory at the beginning of your program. Yeah, that would be even faster because you could run it overnight on some big, long, horrible problem and then save it. But what are we doing at that point? We're executing your function and writing the set of all possible values, right, all inputs and the resulting outputs to file. And now when you want to run your program, instead of actually executing the code, you're just looking it up in a big lookup file, right? Which you can do for pretty much anything. We don't need to write a sine function that uses the Taylor series and does factorials divided into other things and so on and so forth. We can just make a file called sine.txt and store all the values that you might want the sine of and the corresponding sine of those angles, and then just search in there for the sine of an argument. That's a perfectly fine function. And if you kind of think about that, is there anything that you can do on a computer that you couldn't just store in a humongous lookup table? I mean, what do? We go to the computer and we type some things and it gives us some results. Couldn't we just have a huge file somewhere that every possible thing that you might type in, it just stores what the result should be? So you could replace all of this programming and hardware and state machines and all this stuff with just a big lookup table. And that's an interesting direction to go in, I think.
Yeah, because an all-knowing being would have to be able to do everything else.
Yeah.
Someone like us could look and find answers to everything.
Absolutely. You can make a chess playing program with a big book, right? Your first chapter is like all the possible first moves that you might make. And for each of those, depending on what move the other person makes, you flip over to the right page of your book and you look up your second move. Yeah. And it's just a big table. Yeah, yeah. Yeah. Yeah, that's really what databases are, right? They're just humongous piles of information. And SQL is a language for being able to access that information using generally relationships. So give me all the rows of my table where the user's grade is bigger than their GPA, right, or something like that. Yeah, so this is one area of my research that I spend a lot of time thinking about, this idea of using lookup tables to store things. That takes you into something called the songline processor, which is this stuff that I've been researching for a few decades. So that's a whole nother topic in itself.
Tell us more.
Tell me more. But yeah, I'll do the pitch for the website. I've probably given you this before.
Just gotta make this YouTube video go viral.
Yeah, there you go.
Probably put a timestamp to this time.
Yeah. So songlinesystems.com is the front page for all this research stuff that I've been doing. And it's all like public domain, open source at this point. I let the patents expire, and all the research papers and notes and everything like that, it's all been scanned, it's all uploaded there. And if anybody's interested in playing with really weird stuff, right, go ahead and take a look. There's videos and papers and all kinds of things. All right, shameless plug. So, from dynamic programming, we're going to move on. We're going to start talking about sorting. Okay, so sorting, right, classic problem in computer science, trying to arrange a collection of things according to some sort of order. So the assumptions are that any two things in our collection can be ordered. We have some kind of relationship like greater than. And any two things we can determine if one is greater than the other. So for numbers, this is just a greater than sign, right, or a less than sign. For strings, it might be something like string compare. But for other things, we could have other kinds of arrangements. And the first sort we usually talk about is bubble sort. And we talked about this in 224, and we touched on this for the word index program. And I think we looked at the video of dancers doing a bubble sort in 224. If not, Google it. But what's the idea of a bubble sort? So you have a set of numbers. And the goal is to find the largest number and have it sink down to the bottom of this list. So we could just go through and find the largest number and discover it's a 9, and then take everything below it and move it up one spot and then copy the 9 down. But we don't want to do too many passes on this data. So here's the idea. Start with the first number and compare it to the number right after it, and make sure those are in the right order relative to each other. Okay, so we want smallest on the top and largest on the bottom. So 2 is smaller than 4, it should be above 4, that's fine. 4 is smaller than 7, that's fine. But 7 and 1, those are in the wrong order. So the 2's fine, the 4's fine, but 7 and 1 should be swapped. So we'll put the 1 where the 7 is and the 7 where the 1 is. And then we continue. We compare the 7 now to the 6, and those are in the wrong order. So we'll put the 6 there and put the 7 down. And now we compare the 7 to the 3, and those are in the wrong order. So we put the 3 here and the 7 down here. And what just happened, the 7 kind of like dropped down past the 1, past the 6, past the 3 to this location. 7 is smaller than 8, so that's fine. 8 is smaller than 9, that's fine. But 9 is bigger than 5. So swap that, and now the 9's at the bottom. Okay, after you've done this once, we know that the largest number is at the bottom, and we can prove that. How? Probably with mathematical induction. So the largest number is at the bottom, and now we have one fewer number to sort. And in the simplest version of a bubble sort, we just repeat that exact process. And after we do this a second time, so the 2, 4, the 4 and the 1 will swap, 6 and the 3 will swap, 7 will stay there, 8 will stay there, 8 and the 5 will swap, and the 9 stays where it was, and now the second largest number is in the second largest position. And so if we have 9 numbers to begin with, if we do this whole thing 8 or 9 times or more, we'll end up with a totally sorted list. Okay, so that's basic bubble sort. You've seen it in 121, we've used it in 224. We don't need to go through all the details of the code, right? But it's a useful sort to think about complexity. So we have something like 4 pass equals 1 to n, where 1 pass is just doing this operation, right? So we need to go for I equals 1 to n, compare element I with element I plus 1, and potentially swap them. So it's a classic pair of nested loops. Inner loop moves one number into its proper position. Okay, the largest number, the second largest, the third largest, and the outer loop does that n times, so that at the end we've got n numbers in the correct place. And so roughly speaking, if we're starting with n numbers, how many times are we going to do this set of code here in the middle of our loops? Generally speaking, n squared. Now, it's not perfect, right? Sometimes we're going to have to swap these two numbers. Sometimes we don't. So this might just involve comparing two numbers, or it might involve comparing numbers and then swapping. So the time it takes to do this can vary depending on our numbers. But that variation in time is overwhelmed by the simple total count of how many times we're going to have to loop through this. And once we have this number in its proper place, we don't really need to go through all 9 numbers. We only really need to sort the first 8 numbers. And once these two numbers are in their proper place, we only really need to sort the first 7 numbers. So we can actually make this something from like 1 to n minus pass, right? And the number of things you have to compare and sort really decreases as you make more passes. But if we ignore that to a first order of approximation, it's really n squared. Now, if we pay attention to this detail, the fact that each pass we're sorting a smaller and smaller list, well, the first time through, this will have length n. The next time, n minus 1. The next time, n minus 2, n minus 3, all the way down to where we have a list of just one number, or maybe 2 numbers. And so the total number of passes is really this sum, which is approximately n times n plus 1 over 2. So it's really n squared plus n over 2. But this is the same as n squared. Why? Because when n gets really big, this becomes less and less relevant. Right? If n is 10, this is 110 over 2, 55 versus 100. It's half as much. But if n is a gazillion, it's a gazillion squared plus a gazillion versus a gazillion squared, right? It's 1 gazillionth difference. So as n gets larger and goes towards infinity, this starts to look more and more like n squared. So even with these details, or the fact that you can check to see if it's sorted, and if it is, you can kick out right away, bubble sort is order n squared. Okay? Not the worst thing in the world, but not really good for large amounts of data, because gazillion squared is a bad thing. Okay, but it's a cool starting point. Did we not see the dancers doing the bubble sort? Okay, we did, good. Oh yeah, there's giraffe sort. I wonder if I have that handy. You do? Maybe you can show that Wednesday.
It's like, it's not exactly the same order as that. It checks, it makes a swap, and then it resets and does it.
Okay.
So it's a little different, but it's still
Same idea.
at heart, I think.
Yeah, Wednesday after Chris Height comes in and talks, you can put your laptop up here. Cool, okay. All right, so 2 other sorts, selection sort and insertion sort. And these are both order n squared, but they feel fundamentally different. I was going to bring in 3x5 cards and do this, and I didn't bring in cards, so we'll fake it, but I'll get some cardboard next time. So selection sort. So here's a list of numbers: 2, 4, 7, 3, 6, 5, 1, 8, 9. And our goal is to put these in order from smallest to largest. Okay, same as usual. Okay, selection sort. Keyword is selection. So select smallest number and add to output and loop. So we start off with our output being empty. And we go through here and we try to find the smallest number. So 2 is the smallest so far. That's smaller than 4, smaller, 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 smaller. Here's a 1 that's smaller than 2. So that's the smallest number. We get to the end. 1 is the smallest number. So we somehow remove that from the list and we add it to our output. And we just do this n times. So now I'll go through our list with the one removed and find the smallest number. Well, that's going to be the 2. So we'll remove that from the list, and we'll add that to our output. Go through again. 4 is the smallest. That's smaller than 7. 3 is smaller than 4. That's bigger, 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 bigger. 3 is the smallest. Remove it from our list. Add it to the output.
What are you replacing those spots in the array?
X's written in blue ink. So there's details here, right? But you get the idea of the basic algorithm. We're choosing which number goes into our output next. And we start by choosing the smallest, and then the next smallest, and the next smallest. And we just plunk them into successive locations in our output. So the sorting operation is really happening in what we choose from the array. Okay? And there's details like how do we remove this thing from the array? Well, you have to tag it somehow. Or you could remove it and squish everything up, but that sounds like it's going to take a lot of time. So, yeah, or
You could do an array, and then the first sweep that you do is find the biggest number and then add 1 to that.
yeah, yeah.
Replace the number.
So I was going to say you could replace it with infinity, which is what that would do basically. So there's different tricks you can use for that. But that varies fundamentally from insertion sort. So insertion sort, you don't do any work in picking your numbers. You start off with the first number, that's a 2, and you put it into the correct spot in your output array. So pick next number and insert into the output in the proper place. So we start off with a 2. Well, there's nothing in our output, so that's what our output looks like. Go on to the 4. Where should that go in our output? Well, it should go after the 2. So there's a 2 and a 4. Go on to the third number. There's a 7. It should go after the 2. It should go after the 4. There's our 7. Go on to our next number. That's a 3. Well, it should come after the 2, but it has to come before the 4. So we put a 3 in there, and we move everything else down. And we keep going. Take the 6, that becomes a 2, 3, 4, 6, 7. So insertion sort, the real sorting operation is taking place when you write into the output. Selection sort, the sorting is taking place when you read from the input. Okay, that's the big difference between the two. So selection, you select in the proper order. Insertion, you insert in the output in the proper order. This one you have to work to find which thing to read, but you do no work in writing it. It just goes on to the end of the output array. This one you do no work in reading, you just read the next thing from the input array, but you have to do some work in placing it in the output. And they're both n squared, right? This one, to find the smallest number is an order n operation. And to put it in the output array is order 1. Just array bracket size equals value. And you have to do n passes, so that's n squared. This one, reading the number from your original array is order 1. You just read the next element in the array. But putting it in the right spot is an order n. Right? You have to go through until you find the spot, and you have to move everything else down and then plunk it in the middle. That's n operations. N passes in both cases, order n squared. So they're the same as bubble sort in terms of complexity. When I'm alphabetizing papers, I had to think about this the first time I asked this. I'm pretty sure I do an insertion sort. I don't know why. But I go through the papers. I take the first paper, and that's already in the right spot. I take the second paper, and I put it before or after the first. Then I take the third paper, and I put it in the right spot with those two papers I've already got. And I'm like pulling papers off the top of the unsorted list and putting them in the right spot in the output one. I don't know if that's universal or if some people find a selection sort easier. I don't know.
I think with the more of the things that you're trying to sort, it's easier to do the insertion.
Yeah. If I had 3 things and I could immediately see this is the first one, I would just grab that. Actually, I do a combination. Because if your last name starts with like W, X, Y, or Z, I usually grab you and I put you in a separate pile. Because 'cause I know that's going to go at the bottom of the pile. So brains are weird things. And then if we've got more than like 15 or 20 papers, then I start doing it in divisions and merge sorting. So we'll talk about merge sort on Wednesday. We'll talk about quick sort. Merge sort is a divide and conquer. Quick sort is a really quirky kind of divide and conquer. Radix sort is just plain quirky. It's kind of like a try. And we'll talk about heaps and heap sort if we have time. So I'll bring in some playing cards or some 3x5 cards, and we'll go through all of these in detail. We'll look at some code. You're not going to have a programming assignment on sorts, unfortunately, but we'll leave that for 223. But we'll go through the concepts, the algorithms, look at some of the details, look at order of complexity, and that will get us through sorting.
When we work with sorting in Java, are you going to have us work with like a GUI or something? Like, are we going to be working with display at all next term?
We're definitely doing GUIs in there. So I don't know if we'll use that for sorting or not. That would be kind of fun. I've actually done that in 222 in some cases.
Some, like rectangles or something.
Yeah, yeah.
Different heights.
Mm-hmm. Yeah, that would be cool. All right, cool. I will see you next time then.
Or giraffes, I don't know.
Or giraffes.